Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is lecture number 9. In the earlier lectures, we have looked into the overview of VLSI Design Flow. This lecture onwards will be going into each individual design task in detail. For the RTL to GDS design flow, the RTL is considered as the starting point, or when we get an RTL, we say that we have started the design flow. Now, in the earlier lectures, we have seen that an RTL is modeled using hardware description languages. Now, among many hardware description languages, Verilog is the most popular. So, in this lecture, we will be looking into some basic concepts related to Verilog. Specifically, in this lecture, we will be first looking into the features of hardware description languages, and then we will be looking into various constructs of Verilog, or basic syntax and semantics of Verilog. Now, let us first understand that what are some distinct features of hardware description languages compared to other high-level programming languages. So, several of the features of hardware description languages are basically same as other high-level programming languages such as C and C++. However, the hardware description languages such as Verilog and VSDL have got distinct or some special features, and these features are required because we want to model hardware, and hardware has got some features which needs to be captured or modeled in a realistic way using these languages. So, what are these features? So, the first feature that a hardware can offer is concurrency, meaning that the computation can be done in parallel. So, let us take an example. Suppose this is a simple circuit, right? It has got two adders. The first one is adding A plus B, while the other one is adding C plus D, right? Now, these two hardware components can work in parallel, meaning that while A is changing, the first adder will produce a result and Z1 will be produced, while if say one of the inputs is out of C and D is changing, that at the same time the other adder will also produce the correct outputs in the parallelly or concurrently. So, this is something distinct to hardware which is not there typically in high-level programming languages, because in other high-level programming languages what the model is that we have a CPU and we have instructions, and instructions goes to the CPU and they are executed in a sequential manner, right. But in hardware we can do computation concurrently, and the hardware description languages must have syntax and semantics to distinguish between parallel and sequential operations. Note that in hardware a sequential operation can also be there. For example, consider this circuit. In this there are two adders. The first one is adding A plus P, the result is produced here as A plus P, and the second adder is adding A plus P and the result A plus B plus C is there or is produced by this circuit, right. But this second adder can do the computation only when the first adder has done the computation, right. So, for example, if A produces or A changes, then the change should be first reflected by the first adder, and once the first adder has done or updated its computation, then only the second adder can produce the result at the final output, or a plus b plus c, or the correct value or the updated value of a plus b plus c will be captured at the output. So, the hardware can be organized in a sequential manner also, in a series manner also, and it can also be organized in a parallel manner, right. So, the most important feature of an hardware description language is that it should have syntax and semantics to distinguish parallel and sequential operations. The second thing that is required for hardware modeling is the notion of time, right. So, we need to describe behavior of the system with respect to time. There may be delays in the signals, and those kind of things we need to model or capture in the hardware description languages. And of course, the notion of concurrency and sequential operations requires some notion of time also. And for modeling hardware, we also need to create waveforms, especially for synchronous circuit, right. In synchronous circuit, there is a clock, right, and we want to model our circuit such that some operation happen at each edge of a clock, right. So, we need to have something which allows us to model this clock in an easy manner, and captures the operations which are controlled by the clock in a realistic manner. So, these kind of features should be there in hardware description language. Then, in hardware description language, since it is capturing hardware, in hardware we are modeling the electronic circuits. There we need to consider about the strength of the signals also. For example, if we have, say, two drivers for this signal Z, right, one driver is A, other is B, right. Now, when there are, say, A and B are producing output, there can be in some situation a conflicting value, right. Now, one is producing, for example, 0, other is producing 1, right. But now there can be the strength of the signal which may decide its final value Z. For example, if 0 is weak and 1 is strong, right. In that case, Z will probably will get a value of 1, right. So, there should be some way of resolution of the conflict, right, when there is a conflict in the operation of values at a signal. The third or the fourth thing that is required for an hardware description language is that it should produce, it should have bit true data types, meaning that when we model our hardware, there can be, say, data bus, and this data bus can contain, say, 32 signals, 32 individual signals. So, sometimes we want to do operation with the entire bus together. For example, if there is this bus, the value of this bus is written from one buffer to another, then we can just say that A is equal to B, in the sense that A is a bus and B is also a bus, right. Or in some cases, we want to do operation of each individual bit, right. For example, we want to mask some bit out of this bus, right. So, or we can want to take a group of them and do some operations, right. So, the behavior of buses should also be modeled, behavior of individual bits also needs to be modeled. So, in a sense that we need various levels of abstraction of the signal, right. Maybe one abstraction level is a bus, and the other abstraction level is a bit of that bus, right. So, the hardware description language should support various kinds of abstraction level of signals. Now, in early 1970s, there was a lot of research regarding the hardware description languages, and many hardware description languages were proposed. Finally, two hardware description languages that became popular were Verilog and VSDL, right. So, these are currently these are the most popular languages which are used for modeling hardware. So, let us look into them briefly, right. So, Verilog was created in 1983-84 at Gateway Design Automation, and the word Verilog is basically derived from two words, verification and logic, right. So, veri from the verification and log from logic, right. Now, as this Verilog word means or may or signify that it is Verilog was initially started for the purpose of verification, right. So, it was started for the purpose of verification using simulation, right. So, the main purpose of this very invention of Verilog was to do very fast kind of simulation, fast simulation. And in early 1980s, there was a simulator which was Verilog-XL, which could do a very fast simulation at that time compared to other existing technologies, right. And this was the first reason why Verilog became popular. Then a tool called design compiler from Synopsys, which could actually do synthesis, logic synthesis using the Verilog language. This was basically developed, and this and the concept of using hardware description language to model a circuit and then automatic transfer of that hardware description model or HDL model to a logic or netlist. This was a concept which was new at that time, and it was efficiently being done by this tool design compiler, and this made it further popular. And another reason why Verilog became popular was because of its simplicity. Simplicity in terms of syntax and semantics, as we will see in today's lecture. So, the syntax of Verilog is very much similar to C, right, and this resonates with the engineers who already knew C, and that is why this Verilog became very popular, and it was first standardized by IEEE in 1995 and then again in 2001 with more updates. Later on, for verification purposes, more features were required, right, and to support that, the features from other languages were borrowed, and a language known as System Verilog, which is a superset of Verilog and with added functionality for design verification, that was proposed and standardized in 2009. Okay. So, currently Verilog and standard System Verilog, these are the most popular hardware description languages for design and verification, and according to one estimate, it almost 80% of the chip designing or digital circuit designing is basically done using Verilog or System Verilog. Another popular language is VHDL. So, VHDL is a short form for VHSIC, hardware description language. Now, VHSIC stands for very high speed integrated circuit. So, this language VHDL was initially started as a documenting language for integrated circuit in 1980s, and it was very popular at that time. And since it was more for documenting purpose, it is very verbose language, and there are strict type checking in VHDL language. So, VHDL was initially standardized by IEEE in 1987 and recently in 2019. So, VHDL is also a popular language for modeling hardware. Now, let us go into the various features of Verilog languages, right. So, before going into the features of Verilog language, let me show one dialogue that from a novel Through the Looking Glass by Lewis Carroll. Right. So, there is a dialogue between Humpty Dumpty and Alice. Right. So, Humpty Dumpty says, when I use a word, Humpty Dumpty said in a rather scornful tone, it means just what I choose it to mean, neither more nor less. Right. Then Alice says, the question is whether you can make words mean different things. So, Humpty Dumpty replies, the question is which is to be the master, that is all. So, this dialogue basically very aptly describes the role of words in conveying ideas, and it also describes the challenges and what opportunities we have in defining words, what they mean. So, with this idea, now let us look into that how the words in Verilog are chosen to basically describe a hardware. So, the word should be chosen such that it can describe the hardware very realistically, as well as it should it should do in a such a way that it does not leads to lot of confusion, meaning that it has to describe the hardware unambiguously, the features of hardware unambiguously, right. So, in today's lecture basically we will be looking into the features, syntax and semantics of Verilog, how these Verilog constructs or Verilog features are used in simulations and synthesis we will be looking in next couple of lectures. So, in this lecture we will be just introducing the constructs of Verilog languages, and then what are the interpretation of these constructs we will be looking in subsequent lectures. So, a Verilog language considers an RTL file or a given file as a stream of lexical tokens. Okay. So, if there is a file, it contains words, characters and so on. So, the Verilog language considers it as a stream of tokens, and this the rules for what are the lexical tokens and so on, these are similar to the C programming languages, and it is case sensitive. This is another point we should note, that Verilog language is case sensitive. Now, what can be the tokens? So, in a given file, what could be the tokens in that file? So, tokens can be of these types. It can be white spaces, comments, keywords, operators, identifiers, numbers and strings. So, now we will be looking at each of these tokens in a little more detail to understand that what is allowed by the language and what is the interpretation. So, white spaces can contain a white space can contain the characters of spaces, right. For example, I write a word, say white space. So, between these two words, this is a space and this is a white space, right. So, the white space can contain characters or spaces. It can also have tabs, new lines and form fields. And what is the role of white space? It is used as a separator for tokens, right. So, we break the Verilog file into various tokens with the help of white spaces. And then what are comments in a Verilog file? So, anything starting with double slash like this, or anything which is enclosed within slash and star and slash and star, these are considered as comments, right. So, nested comments are not allowed. So, this is comment, one line comment, right. If we need one line comment, we just put like this and add whatever the comment is. And if we want a block of comment, then we can say, start with this, right, give our comment, right, and then end it, right. So, this is a block comment. Okay. So, what are keywords in Verilog? So, these are keywords are basically reserved words for the Verilog language, and what. So, these reserved words are always in lower case, right, as per Verilog standard or Verilog syntax, it all the reserved keywords are in lower case. For example, the keywords are module, input, output, initial, begin, end, always, end module, and there are many other keywords of the languages. So, we will be looking at those keywords as we proceed in the lecture. Then there are operators. Operators are predefined sequences of 1, 2 or 3 characters used in expression. Okay. For example, exclamation mark, plus, manners, ampersand and equal and not equal kind of. So, we will be looking into these operators in more details later in this lecture. Then we should understand what are identifiers in Verilog. So, identifiers are unique names given to an object, right, so that it can be referred to in the Verilog code, right. And for what object we want to give unique name? We want to give unique name to say modules, ports, nets, registers, functions. So, whatever RTL entities are there or design entities are there, for them we want to give a name to them, so that we can refer it later in the code, right, for various purposes, right. So, what are the rules for the identifiers? So, the first rule is that it should start with any alphabet, either small letter A to Z or capital letter A to Z, or it can start with an underscore. So, an identifier must start with only these things, right, and in between it can have numbers also. So, subsequent characters can be, in addition to the alphabets and underscore, it can have numbers and dollars also, right. For example, I give my name to a module as say my module underscore top. So, this is an identifier, right. So, this module we can reuse in our code wherever required, right, to refer it. Similarly, register underscore 123 is an identifier, right. Now, these identifiers are case sensitive, meaning that if I write capital NET underscore 1, this is a separate identifier, and if we write small letter NET underscore 1, this is a distinct from the first one, right. So, the identifiers are case sensitive, and the maximum size of the identifier allowed by the language is 1024, meaning that the tool which support Verilog language, they must support at least 1024 number of characters in a identifier, right. Now, the tools can support more than that also, there is no problem, but at least they must support 1024. So, what it means for a designer who is writing a code or writing an Verilog code. So, the designer can use an identifier which should typically use identifiers of size less than 1024, because we are not sure that whether all the tools that will be used in the design flow will be supporting size more than 1024 or not. So, to be on the safe side, we should always restrict our identifiers to be less than 1024 characters. Now, there can be something known as escaped identifiers. Any character can be used in an identifier by escaping the identifier. It means that in addition to the characters that we have said that these are allowed in an identifier, If we want to add use other characters, can we use it? Yes, we can use it, but in that case there is some rule we have to follow. So what is the rule? The rule is that if we want to use special characters in our identifier, we have to start that with a backslash, right? We have to start with a backslash and end with a white space, meaning space, tab or something like that, right? So these are known as escaped identifiers. For example, suppose I wanted to use the word, the characters bracket, plus, bracket and star, right? So these characters are not allowed in identifiers, right? But if we want to use it for because suppose this is adding more readability to my code, in that case I should start the identifier with a backslash and end with a space. So a space is not visible here, there is a space after this, right? So the tool will treat the name as net underscore a plus b star c, right? So it will remove this backslash and also the ending white space, right? So this is just for understanding of the tool that this escaped identifier is starting and ending, right? So whatever is between them, the tool will treat the identifier name as such without the preceding backslash and without the ending space. Then what are the numbers in Verilog? So it can be integers or real numbers. So it is when we write numbers in our code, we should use a convenient, we should make it, we should write in a format which is convenient to us, and also it is readable for others to read the code. Note that once we write the code, it is not only for us that we are writing the code. Our code that we will be writing, it will be maybe used by some other group, or will be debugged by some other group and so on, right? So whenever we write a code, we should look into the readability part also, meaning that whether our code is understandable to the other person who will be using the code, okay? So when we write a code, we should use a representation which is convenient and readable, but tools internally will convert it into a sequence of bits, right? So when we write, we can use either decimal notation, hexadecimal, octal, binary, any format we can use for integers, right? And then but the tool internally will convert it into a sequence of bits, right? In traditional format, like we can write an integer either in the traditional format like say 169 minus 123 and so on. This is allowed, right? Or if we choose to define the base and size and other things, we can use this format, okay? So what is this format? So the first character is minus, right? It is for the negative sign, it is optional, right? And then this we have the size, right? The size defines the number of bits, default is 32, and base defines that what is the base of the number. It can be binary. So for that we should use the let character small b or capital B, or it can be octal, which can be defined by O or capital O. Decimal we can use D, and hexadecimal H. So we have to define this base using these characters only, right? And the final thing is the value of the number. So let's take a few examples. So if we write just one, right? So the internal representation will be 0 0 0 0 and then final will be 1. So internally it will, since we have not specified the size, it will be treating it as 32-bit, and that is why all these zeros will be added. Now if we write one tick B1, then we are saying that okay, there is no negative sign, so there is a positive number. Then 1 defines the size of this number. So 1 means that it is of only 1 bit, right? And B defines that it is a binary number, it is not octal or decimal and so on. And 1 defines the number. So 1 tick B1 is just one number which is Boolean number 1, right? and then the third number is 8 tick HA1. So, 8 means that it is of 8 bits, right. If the size is 8 bits, H means that it is a hexadecimal number, and A1 basically is the number. So, for A we have 1010. So, A in hexadecimal is 1010 in binary, and for 1 we have 0001. So, this will be the representation, internal representation. Now, for 6 tick O71, right. In this case we are saying that the size is 6 bit, right, size is 6 bit. It is an octal number, O means it is an octal number. Now, for 7, the octal 7 is equal to 111 in binary, right, and 1 is 001. So, this is the number, internal representation of the number. Now, there can be complicated scenarios of writing the integers. So, these are the rules. So, now for hexadecimal octal binary constants, x, small x or capital X represent the unknown or do not care value, right, and Z and capital Z question mark represent the high impedance value. Now, when an high impedance is do not care, it is better to write question mark. So, it distinguishes that it is basically do not care and not a high impedance, or a high impedance which is should be treated as do not care, right. For example, this is the number 8 tick B 100 Z 00 question mark 1. So, here question mark is same as Z, right. Internally it will be treated same as Z or high impedance value. Now, when size is smaller than value, then leftmost bits from the value are truncated, right. So, what it means is that suppose we give a size value say 6, which is smaller than the value it has, right. So, the value it is here, it is in hexadecimal, right. So, and we are writing 8 8. So, in hexadecimal 8 is equal, in binary it is 1000 for the first 8 and then 1000 for the next 8, right. But we are saying that represent it in only 6 bits, not in 8 bits, it has got 8 bits. So, what the tool will do is that it will simply truncate the leftmost bits are truncated, right. So, these 2 bits will be truncated and the internal representation will be 001 000. Now, other situation can be when the size is greater than the value, then leftmost bits are filled with either 0 if leftmost bit value is 0 or 1, or it will be filled with Z if the leftmost bit is Z, or it will be filled with X if the leftmost bit is X, right. So, if the size is greater than the value, right, so it needs to add some number. So, these are the rules which defines that how to add those numbers, right. So, for example, we take a number which should be represented in 8 bits, right, and it should be in binary, and the numbers are the value is given just 1 1, right. So, in that case, since the leftmost bit is 1, the other leftmost bit, that is the ones which are not specified, those are taken as 0. In the other case, if we say Z1, right, so Z1 is there for 2 bits, right. Now, what are the other bits that will be padded or will be put before this number on the left hand side? All will be Z. Why? Because the leftmost bit was Z in this case, right. Now, we can add underscore in the middle of the number to enhance the readability. For example, if your number is very long, right, we can break it into smaller parts by adding underscore, right. So, for example, if it is an 8 bit, we can write as 4 bit and separated by underscore, and this underscore will be simply ignored by the tool and the number will be treated as number without having that underscore. This is just for readability. Now, negative numbers are internally represented in 2's complement. For example, if the number is say minus 8 tick D 6, right, and we want to represent it in 2's complement, right. So, first the number, we have to take the binary equivalent of number 6, which is 1 1 0, and the size is of 8 bits, right. So, we have to pad the numbers with 8 bits to make it 8 bits. Then we take first the ones complement, that is 1 1 1 1 1 0 0 1, and then add 1 to it. So, it becomes 0 1 0 1 and 4 ones, right. So, this is the internal representation of minus 8 tick D6. So, in Verilog, the real numbers can be represented in decimal form like we normally do. So, for example, we can write a real number as 3.14159, or we can choose the scientific notation like 2.99E8, right. We have mantissa and exponent part separate. Internally, real numbers are represented in IEEE standard for double precision floating point numbers. And Verilog supports string also, and string is a sequence of characters enclosed by double quotes and contained on a single line. For example, this is a string, right. Now, internally the string will be represented by its corresponding value in with each character being represented by a 8-bit ASCII equivalent of it. For example, the word or the string hello will be represented internally as H, capital H will be represented by ASCII equivalent of H, right, in 8 bits. Then similarly, E will be represented or for the ASCII equivalent of small e, and so on. So, internally the string will be represented by the ASCII representations of each of the characters in that string. Now, let us look at what are the data values and data types in Verilog. So, Verilog supports 4 valued data, right. So, this is an important thing, because typically we associate digital circuits, digital systems with binary values, meaning 0 and 1, but Verilog supports 4 valued logic or 4 valued data. And what are they? So, first one is of course 0, which is equivalent to Boolean 0 and logic false. 1 is equivalent to logic true or Boolean 1, and the third is x, which is unknown value, right, and z, which is a high impedance state. So, these are 4 values which are supported for a signal or for a data. And what are data types in Verilog? So, there are 2 primary types. The first one is net and the second type is variable. Now, let us look into what is a net. So, net represents structural connections, right. Whenever we say net, it is a kind of wire, right, and it cannot store value. It has nothing to store value, it only connects entities in the design, right. So, see, these nets are like wires, right. So, and the keywords to define a net is wire, supply 0, supply 1, WAN and WOR, right. So, these are the keywords. For example, we can say that wire W1, W2 or wire W3 is equal to 1 tick P1, and then we can say this ground is the name of a wire, VDD is the name of the wire, and the type is supply 0. It can be used to model logic 1, right, or something which is connected directly to the supply voltage. 0, sorry, supply 0 is to model ground, right, rather than the logic 1, it is related to logic 0, right, and supply 1 is for logic 1, or it is used to model VDD. And the second type data in Verilog is variable. Now, variables are the elements that store value in simulation, and these can be declared using keyword reg, R-E-G, reg, right. So, it stores the last assigned value until changed by another assignment. So, reg stores the last value until its value gets changed, right. Example is reg R1, R2. So, these are variables, right. And these reg basically work similar to a variable that we have in, say, other programming languages. Its value, it stores value, and until and unless we change it, it keeps the old value. So, we can assign reg in procedural blocks. What are procedural blocks? We will see. So, reg can model flip flops, latches, and also combinational elements. Now, this is important. So, many times new programmer in Verilog consider reg similar as register, and they think that it is something to do with memory or flip flops, right. So, reg is a keyword which is there to define a variable. Finally, this variable, will it be synthesized to a flip flop or a combinational circuit or to a latch, that will be based on how this reg is basically used inside the Verilog code. It need not always be synthesized to flip flop or memory element. It can also be synthesized to more combinational elements. So, reg is not equivalent to a flip flop in the hardware, right. That is what I want to point out, because this kind of mistake novice programmers make. Now, Verilog also supports vectors and arrays. Now, nets and variables, if we declare, they are by default they are of 1 bit wide, and they are known as scalar. Now, in the Verilog also supports vectors and arrays, right. So, we can declare a vector by preceding the declaration with vector definition in the following format. So, before the declaration, we can give, or before the identifier, we can give this left range and right range separated by colon, and then in a square bracket, for example 7 to 0, right. So, this will be defining a vector, right. So, left range is the most significant bit, this one is the most significant bit, and this one is the least significant bit. For example, we have said 31 to 0 data bus or 7 to 0 address bus. So, these are examples of vectors. Now, in this vector, what we can do is that we can select a bit of a vector by specifying the address within the square bracket like this, or we can select a portion of a vector by specifying the range of MSB and LSB separated by a column. For example, in this, from this data bus, if we want to get the 4th bit, we just write data bus and then select within square bracket the bit position, right. So, 4th in this case. Similarly, if we want to get part of a bus, then we can say address bus 3 to 0. So, it will give all the bits from 0, 1, 2, 3 in all these positions, right. So, it will give the bits in that position in the address bus when we use this construct. Now, Verilog also supports arrays, and it can be used for grouping elements into multi-dimensional objects. And so, many a times, for example, when we are trying to model memory, right, in there we can want to group together entities in some manner. So, if we want to do those kind of grouping, then we can use arrays. So, the difference between vectors and arrays in terms of syntax is that we specify its range after the identifier, right. So, for the vector it was before the identifier, for arrays it is after the identifier. For example, if we write reg r 15 to 0, then it is basically grouping together 1 bit register r and 16 of them, right, starting from 0 to 15, that are 16 in the group, right. Similarly, we can have more than one dimension. So, here it is a 2-dimensional array which is defined here, right, of size 10 cross 10. So, this defines a matrix of size 10 cross 10. So, we have seen a few constructs of Verilog language in this lectures. Now, we will be looking at more such constructs in the next lecture. Thank you very much.